bursting the moment it leaves the ground. Within 24 hours, the starch inside begins breaking down. Bacteria attack. Enzymes activate. The root turns black and worthless. So the factory designed to process 1 million cassava roots per day is not just a production facility. It is a race against decomposition, where every minute of delay costs money, where machines operate at speeds that seem reckless until you understand the alternative. Welcome to industrial tapioca starch production, where biology sets a countdown timer, and technology fights to beat it.
Cassava is a root crop grown across tropical regions: Nigeria, Thailand, Brazil, Vietnam. It looks unremarkable: brown skin, white flesh inside. But that flesh contains starch granules, tiny particles invisible to the naked eye. And extracting those particles at scale requires destroying the root completely, breaking every cell, releasing every granule, then separating starch from fiber and protein and water, all before the root deteriorates beyond use. The window is 48 hours maximum. Most factories process within 24. Some aim for 12. Because cassava waits for no one. The process begins before dawn. Trucks arrive loaded with freshly harvested roots, tons of them, dumped into receiving yards. Workers inspect quickly, looking for rot, checking for damage. Any root showing black spots gets rejected immediately. No second chances. The clock started ticking hours ago in the fields. Every load gets weighed, not just for payment, but for starch content measurement. They use a specific gravity test. Denser roots contain more starch, less water, higher value. The measurement takes seconds. Then the roots move forward into the first stage, cleaning. The dry sieve rotates constantly. A massive drum with spiral ridges inside. Cassava roots tumble through. Dirt falls away. Loose peels separate. Small stones drop through gaps. The machine does not use water yet. Dry cleaning first. This removes the bulk of field debris without creating mud, without wasting water. The roots emerge cleaner, ready for washing, but still covered in a layer of soil and residual peel that must be removed before processing can begin. Into the paddle washer. Here, water finally enters the system. Jets spray from multiple angles. Paddles rotate, scrubbing the roots against each other. The mechanical action combined with water pressure removes the remaining soil, loosens the outer peel. Cassava skin is thin, not like potato. It comes off easier, but must be removed completely. Any peel contamination affects final starch color, makes it darker, less valuable. The washing station runs continuously. Roots in, clean, roots out. Water recycles through filtration. Nothing stops, because time is the enemy here. Most people never see what happens next. Clean roots drop onto conveyor belts, moving toward the cutting machine. This is where size reduction begins. Cassava roots are irregular, some thick, some thin, some curved. The cutting machine does not care. Rotating blades chop everything into chunks, roughly 1 to 2 inches, small enough for the next stage, but not pulverized yet. The chunks still hold their structure, cell walls intact, starch trapped inside. That changes in the next room, where the rasper waits. If the next machine slows down, everything behind it starts rotting in real time. The rasper is the heart of this operation, a machine that sounds violent because it is. High-speed rotating drum, covered in saw blades. Hundreds of them, arranged in precise patterns. The cassava chunks drop in from above, hit those spinning blades at extreme velocity. The impact is immediate, total. The blades do not just cut, they shred, pulverize, destroy the cellular structure completely. In milliseconds, each chunk becomes slurry, a wet paste of destroyed cassava tissue. And this is where the starch releases. Tiny granules freed from broken cells, suspended in liquid. This is the critical moment, because if the rasper fails to break the cells completely, the starch stays trapped, wasted, lost in the fiber. The operator running this machine has done it for 12 years. He knows the sound.
The pitch changes when blades dull. The vibration shifts when feed rate is wrong. His job is to catch problems before they stop the line, because stopping means everything behind starts rotting. Modern raspers achieve extraction rates often above 90%, meaning the vast majority of cells get destroyed. Starch released. That number matters enormously. Even small differences in breakage rate mean significant yield loss. On industrial scale, that translates to massive financial impact. So the rasper operates at speeds that seem dangerous. The rotor spins at rates measured in thousands of rotations per minute. The saw blades are clamped with extreme force. If one breaks loose at that speed, it becomes a projectile, which is why the entire machine is enclosed in heavy steel housing, reinforced. No windows, just input and output. The sound inside is deafening, a continuous roar of metal on organic matter. People call it the terrifying rasping, because it sounds like a machine losing control while doing the most controlled thing in the plant.
But here is what most people miss. That violence is precision. Those saw blades are manufactured to exact specifications. The spacing between blades is calculated. The angle of attack is engineered. The screen mesh at the bottom of the drum is measured in fractions of millimeters. Everything designed to maximize cell breakage while minimizing fiber damage that would complicate separation later. This is not chaos. This is controlled destruction. Biology being forced to release what technology needs. The rasper output is slurry, wet, grey-white, containing starch granules, fiber fragments, protein, cell fluid, all mixed together. This slurry gets pumped immediately to the separation stage. No storage, no delay. Because even in slurry form, the cassava is still deteriorating. Enzymes are still active. The clock still ticks. The separation must happen fast. This is where millions are lost if done wrong. First stage separation uses centrifugal sieves. Rotating screens. The slurry gets pumped onto these screens while they spin. Centrifugal force pushes liquid and fine particles through the mesh. Fiber too large to pass stays on the screen. Gets washed. Pushed to the edge, collected separately. But this is not single-pass filtration. The system uses 3 stages in series, each with finer mesh. First sieve removes coarse fiber. Second removes medium fiber. Third catches fine fiber that almost made it through. The separated fiber is not waste. It gets dehydrated and sold as animal feed. Nothing is thrown away in this industry. Every component has value. The starch slurry coming out of the centrifugal sieves still contains problems. Sand particles, mud that pass through the mesh. These are heavier than starch granules, so they get removed by gravity separation. The slurry enters a desanding cyclone, spins at high velocity. Heavy particles sink to the bottom, removed continuously. Clean starch slurry flows from the top. Simple physics, but critical. Sand in the final product is unacceptable. Ruins texture, damages equipment downstream. So desanding is mandatory, not optional. Now comes refining. This is where pure starch separates from everything else. The hydrocyclone station. A series of cone-shaped chambers arranged in multiple stages, sometimes 16 stages, sometimes more. The starch slurry enters at one end. Clean water enters from the opposite end. They meet in the middle, flow in opposite directions. Counter-current washing. This is genius engineering. As the slurry moves through each cyclone stage, proteins wash away. Soluble materials dissolve out. What remains gets progressively purer. Starch concentration increases. By the final stage, the liquid coming out is almost pure starch milk. White, smooth, still liquid, but highly concentrated. Clean enough to be starch, not clean enough to be a product. However, that starch milk contains too much water for drying, about 60% moisture. Drying that directly would take forever, cost massive energy. So dewatering happens first. The starch milk gets pumped into peeler centrifuges, massive machines rotating at thousands of RPM.
Centrifugal force separates liquid from solid. The water gets thrown outward, drained away. The starch forms a cake against the machine wall. Scraper blades peel it off continuously, hence the name. The wet starch coming out contains about 40% moisture. Much better. Now drying becomes feasible.
The flash dryer is a vertical tower. Hot air enters at extreme temperatures. The wet starch gets blown into this tower as fine particles. They fall through the hot air stream. Water evaporates rapidly. In seconds, the particles dry to the target moisture content. The physics here is brutal. The high-temperature air would damage the starch if contact time was longer. But the particles are so small and falling so fast that they dry before degradation occurs. Flash drying, named for the speed. The dried starch gets collected at the bottom by a cyclone separator. Still hot. Cooled immediately to prevent clumping. After cooling, the starch goes through final sieving, removing any oversized particles, any remaining impurities. The sieve mesh is extremely fine. Only properly sized starch granules pass through. Everything else gets recycled back through the system. What comes out is finished product. Pure white, fine texture, ready for packaging. But before packaging, every batch gets tested. This step looks simple. It is not. Quality control checks multiple parameters. Moisture content, tested with refractometers, must be below 14%. Whiteness, measured against standardized charts, must meet grade specifications. Viscosity, tested in solution. Purity, screened for protein residue. Fiber content, microbial contamination. Only batches passing every test get approved. Failed batches get downgraded, sold to industrial users who accept lower grades, or reprocessed. Nothing gets wasted. Even failures have markets. Approved starch moves to packaging. Automated filling machines. Laser sensors. Weighing each bag to the gram. The line packages thousands of bags per hour. 20-kilogram bags mostly. Some 50-kilogram for industrial buyers. Each bag gets batch codes, production date, quality grade, expiration information. Then stacked on pallets, wrapped, ready for shipping. The entire process, from raw root to packaged starch, takes 10 to 15 minutes. That speed is not a luxury, it is survival. Here is the math that keeps managers awake at night. If hundreds of tons of intake sit an extra day, even a small percentage of starch loss becomes a truckload of money, literally. In a plant like this, that's not a metaphor, because here is the reality. A large processing plant can handle hundreds of tons of raw material daily. If that material sits for 2 days instead of 1, the losses are catastrophic. Starch content drops significantly. Color darkens. Quality falls. Market value plummets. So these facilities operate as continuous flow systems. No storage tanks, no holding areas. Material keeps moving, always. The moment cassava enters, it begins its journey to becoming starch. Any delay anywhere ripples through the entire system, causes backup, creates bottlenecks, ruins batches. This is why major factories run 24 hours. 3 shifts, continuous operation. The machines never fully stop. Maintenance happens during brief cleaning cycles. Parts get replaced on the fly. Broken components get swapped while the line keeps running. The economics demand it. Cassava farming is seasonal in some regions. When harvest happens, the roots arrive in massive quantities. The factory must process everything, fast, or farmers find other buyers, other processors. Lose the supply and the factory sits idle. Cannot recover. The scale is staggering when you think about it. Processing capacity measured in millions of roots daily. Arriving on trucks. Getting cleaned, chopped, rasped, separated, refined, dried, packaged, shipped. The logistics alone require military precision. Truck schedules, labor shifts, machine maintenance windows, quality checks, everything coordinated. Because one failure point stops everything. The rasper breaks and the line halts. Cassava backs up, starts rotting in the yard. Losses mount by the hour. So preventive maintenance is obsessive.
Spare parts kept ready, backup systems installed, redundancy built in, because downtime in large plants is measured in tens of thousands of dollars per hour.
The environmental impact gets managed too. Wastewater from washing and processing contains organic matter, high BOD, biological oxygen demand, cannot be dumped directly into rivers, so treatment plants operate alongside the factory. Settling ponds, bacterial digestion. The water gets cleaned, recycled where possible. What cannot be recycled gets treated to safe levels before discharge. The fiber waste becomes animal feed. The cassava peels go to composting. Some factories even generate biogas from organic waste, methane for power generation, turning waste into fuel. Industrial ecology in practice. Worker safety is another constant concern. The rasper is obvious danger, but other risks exist. Hot steam from dryers, high-pressure pumps, rotating machinery everywhere, wet floors, chemical cleaning agents. So safety protocols are strict. Protective equipment mandatory. Guards on all machines. Emergency stops accessible. Training programs continuous. Because a processing plant is fundamentally a dangerous place. Speed and heavy machinery make an unforgiving combination. Attention must stay constant. The technology keeps evolving. Sensors monitoring every stage. Automated adjustments. Real-time quality checks. This reduces error, increases consistency, but requires skilled workers who understand both cassava biology and machine mechanics. Training takes months. Experience takes years. Competition drives constant efficiency improvements. New rasper designs, better centrifuges, more efficient dryers. Every percentage point of yield matters. And tapioca starch is not one product. Food grade, industrial grade, modified starch, each has different specs. The same factory often switches between grades, adjusting systems, running cleaning cycles. This flexibility keeps plants profitable when markets shift. Modern large-scale plants require tens of millions in capital. Stable power, water access, transportation infrastructure. So production concentrates where prerequisites exist. Creates industrial clusters, entire regions specializing in cassava processing. But the fundamental constraint never changes. Biology sets a countdown. 24 hours from harvest to rot. Technology races to beat it. From root to powder. From field to factory to store shelf. Tapioca starch is in more products than most people realize. Thickening agent in soups. Binding agent in processed meats. Paper coating. Textile sizing. Adhesive production. Biodegradable plastics. The applications are endless. Global consumption runs into millions of tons annually. And it all starts with cassava roots, deteriorating from the moment of harvest, racing against time, processed by machines that destroy with precision, separated by physics, dried by superheated air, quality checked by sensors, packaged by automation. An industrial system built around one biological fact. In a plant this size, an hour of delay can mean tens of thousands of dollars in lost yield. Every day, the global industry processes enough cassava to fill thousands of shipping containers lined up portside. The race never stops. The clock never pauses. Somewhere on the factory floor, the